So in today's talk, what I'm going to do is to present our work on energy efficient and security for the AGI applications. AGI is a very wide range of applications where we are integrating artificial intelligence, machine learning into end user systems. So I'll be talking about architectures, systems overall, what are the challenges, what are the different methods, and then the applications that we are developing in our lab. This research has been funded by various sources like Center of Cybersecurity, Center of Artificial Intelligence Robotics, Center of Quantum and Topological Systems, and Center of Smart Cities at 𝗚𝗏 Abu Dhabi. And this is the joint work done at different team members in my group in 𝗚𝗏 Abu Dhabi and 𝗚𝗏 Tandem. Without further delay, I'll just start my talk and give you an overall overview of the challenges. We all know that now machine learning or AI, like in general form, is kind of a de facto standard to process data to predict, derive short-term, long-term predictions. In various different domains that we call them in general smart cyber physical systems, because there is a cyber component and there is a physical component like automobiles, like robotics, as well as the complete cyber components like in our smart homes and healthcare devices. And when we have to implement these kind of systems, what we need very tight performance on extremely low power budget and extremely low energy efficiency. The applications are widespread, like we know that even in an autonomous vehicle or a smart autonomous mobile robot, there are like numerous number of applications which require deep neural networks or even large language models nowadays also on the robots, ranging from collision avoidance, lane detection, and things like that. And we all know that classification is a very saturated problem. It has been widely explored. The modern problems are related to segmentation and detection, and then of course, in terms of online learning and things like that. When we go further, we have seen that these applications can be in different domains like financial sectors, medical imaging and things like that, as well as also like medical clinical support systems and of course games are one of the prominent ones also. This is like a result from our a recent project which is funded by the Multiple Sclerosis Society, where we are detecting the MS lesions in 3D voxel of an MRI image, and then we are also deriving the lesion growth and suppression over the period of time. This is typically called a longitudinal analysis, just to give you an idea that how valuable it would be, and this is very beneficial for the neurologists and neurosurgeons as well as radiologists to very quickly analyze the underlying diseases and issues in medical images. So in general, machine learning and AI can be extremely helpful. The challenges that we as designers face are primarily the resource constraint embedded systems, because many of the applications that we are building up are extremely tight in terms of size, computer memory, resources, and that's relative to the complexity of the modern ML applications. So just to give you an idea, this is an emerging trend of embodied AI, which basically means enabling advanced AI on robotics. Typically these are like called AI agents, and they have certain properties that make them things working in embodied form. For example, there is a wide range of perceptual inputs. You have multiple different cameras, as well as lidar and other kind of sensors. Through these sensors, these robots are perceiving the environment around them, what we call is a world model, which basically means they are building up an abstract representation of their surroundings, localizing them, and then they are interacting with the world, which basically means that it could even be a VLA, like vision language action kind of model, or it could also be an imitation learning based stuff, and they are interacting with the humans and they are learning on the fly, and maybe there's a reinforcement learning implemented on the loop for them to continuously learn different different things. And they have a goal, and they are learning towards a goal. For example, you can give a command, hey Nemo, can you fetch me a packet of chips from the kitchen, and then the robot will automatically do the path planning, navigation. If the map is not perfect, then it will also build the map and then complete the task. Now, instead of being explicitly programmed, it can also learn the policy itself, because the large language models, if they have sufficient amount of data trained, then they can also generate the policy for the robot. And the robot can also do the reasoning that why it has to take route 1 and why not the route 2, like we humans reason, for example, to find the shortest path or to find the path with the less congestion. So in general, if you imagine that there are so many different types of machine learning models running on one small mobile robot, then you can already imagine that the challenge of packing those models under low complexity is a big challenge again. And of course, when generative AI, pretty much everyone, I'm pretty sure, sitting in the room already knows. You guys are already extensively using ChatGPT, Claude, or other kind of DeepSeek-like services. There are also video generation services like Sora, Wen, Midjourney, and Runway kind of stuff. But more importantly, there are also emerging trends in code generation. For example, Cursor, GitHub Copilot, and those kind of stuff. They are extensively being used nowadays for automatically generating your code programs. And ChatGPT itself also really good in code generation. Claude and Quen definitely are very well at the top of the leaderboard in terms of code generation, and they are very specific application code generation that there are other kind of leaderboards available. So what really is very interesting nowadays for the hardware community is the emergence of the large language models to automatically generate the hardware code, which basically means that even if you are not a chip designer, you can actually give your specification to a large language model and it can generate the RTL specification for you. So overall, across different global sites, New York University is one of the leading effort, like having the leading effort in automatic chip generation using generative AI tools and stuff, and there is also a wide range of interest from different companies like Synopsys, Cadence, which are the building of this thing. So eventually, all in all, if I want to summarize, there is a lot of new tools coming up which can solve your problems very easily nowadays. What we are missing is actually ML AI engineering, which basically means that how do you use these tools efficiently to build up the larger system very quickly, how to test them, how to deploy them. And I think that's where the next generation of skill set is. Having said that, the power consumption challenge is extremely important to be understood. We already know that there is kind of criticism on the AI community that they are burning too much power. Even the enterprises are buying or acquiring different power grids. There was an earlier study in Nature Machine Learning that a machine learning model actually can consume more than 5 times than a car actually that is consuming. And now if you look at the latest trends, and this was only for the transform models, and now you can see that the GPT-3 model data center emissions using Amazon services, you can see it's extremely high. The models are growing in terms of complexity and their size, which means the power to train one large, for example, GPT model, GPT-5, GPT-4, or even the latest versions is extremely high, and I think we just cannot imagine that how large it can be. And it's not only the power that we are spending in training, but it's also the power that we are spending in inference. Imagine training is only done by enterprises, so they can acquire power, they can buy everything, or whoever is building up their own foundation model, they can put together a power grid and then train that. But imagine that there is 90% of the systems on the planet are actually edge devices, and we are using them massively in inference. So how much power we all collectively are consuming? So we have to be a bit cautious about that as well. Though a power of a single device may not sound very high to you, but there is a. So yesterday I was actually on a panel for exactly the same problem on CO2 emission, renewable energy or clean energy versus AI. employment in different countries and stuff like that. And there are very interesting discussions that the community is these days doing, that how do you incorporate green technologies when, for example, putting together a compute center for AI training, AI foundation model training, or also building of the energy efficient accelerators for extremely low power inference and things like that. Now, again, let me give you an idea. ResNet 50, which was a milestone in image-based classification, Megatron, which was one of the earliest generation of library transformers, it was more than 2000x complex. In ResNet, it was already in 2019. Within 2 years, GPT-3 was already 90,000x, and within 1 to 2 years, it's already orders of magnitude more complex than that. So if you look at this, this is a super exponential complexity at which we are going, and that's why you can already see that after ResNet 50, the training actually got out of the head of a normal person. Even training a transformer using a NAS, no one can use, because you need to really do it extensive NAS for that to get to the optimal model. It's a neural architecture search. So this basically means that the modern trend is basically the foundation models or the advanced ML models are built by the enterprises, and the smaller companies or the smaller organizations are primarily doing efficient fine-tuning and RAG systems to build up their own systems. So that's where I call the AI engineering is extremely important nowadays. On the other side, there are also a lot of improvements in the underlying hardware architectures. Our GPUs are getting better and better with every generation. If you look at the modern GPUs landscape, they are having a lot of tensor cores, which are very different from the traditional GPU cores that they were having. And now even the tensor cores are in a low precision, like 8-bit, 4-bit kind of stuff. Cerebras released one of the world's first wafer scale chip. Now they have, I think, this generation 2 or generation 3 already, which is much larger than a GPU. And what it does is that instead of communicating across multiple GPUs, you can actually offload the training on these kind of stuff. Now, effectively, if you look at the Autonomous Systems Community Challenge, what they are striving for is basically to put together a brain in a robot or in any kind of autonomous system, but that chip should not consume more than a human brain if you want to get the same type of learning. Although the chips that we are typically inserting due to their cooling factors typically operate in the range of few watts. Below 10 watt is the ideal one. But even if you want to go and we say that we want to be as intelligent as humans, and we are very good in progressive learning, which the modern ML systems are not, then we only need to do that in 20 watts, while these data centers are actually requiring a full power grid. So there is orders of magnitude, at least 3 to 4 orders of magnitude efficiency gap, and that's great news, because in general there is a lot of research and development challenges, and there is a lot of research that has to be done in order to really build true autonomous systems which can think and operate at the same power envelope. Now, just to give you a few future science kind of stuff, I think the future of AI is very bright. If you guys are pursuing your career in AI and machine learning, there is plenty of job which is going to be created in future. And the reason is because pretty much every company is now stepping into that, how their services can be made advanced using machine learning and stuff like that. So Stargate, I think pretty much everyone knows, this is one of the largest initiatives which is done started by US. Many different enterprises in US like OpenAI, Microsoft, NVIDIA have joined hands in that. And the Stargate has a UE version, also because it's a massive investment done by UE. So US UE Stargate initiative is actually going to build a strategic national infrastructure, which basically means that there is a lot of application of machine learning and AI being deployed in every sector here, and there is a strategic agenda that in general we want to become the AI leading company, which is great also because it's very close in the vicinity in Pakistan, and a lot of companies are stepping into the financial sector here as an external entity, and then there's a great potential to grow in terms of entrepreneurship also here. Now, having said that, performance and energy efficiency are two very important stuff, but when you want to deploy them in your systems, robustness is another key point that we have to look into. And in that term, the security, safety, validation, all these are very important goals. So if you look at this, these are like some of the crashes which have been reported for the earlier generation of the autonomous vehicles, and there is also this hacking of the mobile phones which was done by showing these pictures or showing the masks. And I just want to show you some of the videos. I guess that's easier. If you look at this video, you can already see that this is the Tesla bots and the Tesla car, and then they just ran a black box attack, which means they're showing a random image to the car, and suddenly the Viper control system of the car is activated. Here they have put three different white patches, and then the car suddenly, when the autopilot was activated, it deflected. It thought there is some object in front of that. And so when this thing was done, it rattled the community that anybody can buy any autonomous system and then can fool into that and then deploy those attacks in the physical world. These perturbations are called physical world perturbations, and they can create a lot of issues. Recently, a very powerful attack called Phantom attack was done, in which someone can actually project something using micro projectors, and then it can fool the Tesla car or any kind of autonomous vehicle or mobile remote also. Here they have projected a stop sign on the advertising screen, and suddenly the car was stopped in the middle of the road, in the middle of the night, and this is also very dangerous. And when they remove this thing, then it starts working. So what a Phantom attack shows actually that you even don't need to perturb the physical environment. All the physical environment perturbation is very easy because we have billboards, we have signboards, we have a lot of other kind of screens, and you can show nice artistic patterns which embedded adversarial noise and control the system. But you can actually do this by using a projector also, and then don't leave a trace of that thing. So how do you design robots machine learning algorithms which are kind of attack proof? So this is a fully great question, because there have been so many different attacks which being produced at training time, at inference time, model stealing attacks, and someone has to defend against that. And this is one of the big areas where our lab has been actively looking into and then working on the practical prototypes that we are building up. So having said that, these were the challenges, and of course there are a lot of other challenges that the overall AI community is facing, and I'm not going through all the challenges, but the ones which are relevant for at least the primary research projects that I'm going to present today, so I did that. So my lab actually is working across the full system stack. We have teams which are working on developing hardware accelerators, deploying them, securing them using logic blocking. We had a project with one of the large industrial chip manufacturer on reliability of these kind of chips, and then how do you basically ensure that the machine learning models can run reliably on the chips which have faults. And these are very common when you're building your own chips. Some parts of the chip are not working, or they're like in critical systems. There is software errors, like even if for example we have a jet fighter plane or a car, they are kind of seen as critical systems. Or if you are deploying these kind of chips in any airborne systems or nuclear plants and things like this, then there's a lot of softwares happening. Then how do you ensure that they are like really error-proof kind of stuff? Security is one of the main concerns of many of these things. I mean, healthcare also has a lot of stuff, but mostly at the moment community is concerned about the mobile robots kind of stuff. For example, someone can fool your quad rope, someone can fool your autonomous vehicle, someone can fool your UAV or UGV. So how do you ensure that those things cannot be hacked into, even using a black box model, and you are not even sure that if the answer you are getting is correct or not? And efficiency, as I said, is the first class citizen in designing these systems, which basically mean that you need to develop intelligent model compression tools like pooling, quantization, hardware awareness, to make sure that your models are actually practical and deployable on the real world systems. This has led to the whole domain of AGI, tiny ML, tiny NLMs, and all those kind of stuff. And ultimately, we work towards the low power optimizations that down to the circuit level, to all the way to the architecture level also. And then we are building up the full scale applications, like we have in-house build of the full ADAS pipeline, which is advanced driver assistance system. That is also the embedded perception pipeline of any mobile robot. We are building up other kind of machine learning models, even also for the emerging area of the quantum computing, we are doing RTL code generation, we are doing neuromorphic continual learning, we are doing a lot of stuff. So I'll give you a sneak preview of some of the methods, and then depending on the time, I can give you a little bit overview of demos of some of the demos that we have built in our lab, and we are showcasing to our industrial partners also. So the ultimate goal of my lab is to do innovative research and bring it to reality, where we are building up TRL4, TRL5 prototypes, and then showcasing it to our external partners to hopefully do some startups or licensing and things like that. This is the overview of my eBrain lab, where most of my researchers are sitting and doing innovative research on machine learning models and design methods. This is the embedded systems lab, where students are doing hands-on work, building a lot of engineering kind of things. And this is my intelligent coordinated autonomous systems lab, where we are doing the full system prototyping. We have a lot of different kind of mobile robots, humanoid. We have aloha, which is like used for generating the data sets for imitation learning. We have like really big scale tank with mobile manipulator, which is used in many different industrial and agricultural kind of way. We have fully scaled down autonomous vehicle kind of prototypes, and we have a lot of small prototypes of the UGVs and a full scale down track of autonomous vehicle and stuff like that. We have several quad rope and 3D fabrication facilities. Small one and a large one is already available under the CTP in the university. Like just to give you an idea, you can see that some of the just very simple robotic stuff that is working on. Here the arm can pick the bottle, can do the operation. The humanoid can actually do walking. Stabilization is done using reinforcement learning. It can maneuver through autonomously in the corridor. The dog can also do a slam, and then localization, can do collision avoidance. And there is again a full stack working on. This is LiDAR based, but we are moving towards a full camera based systems because we want to deploy this whole pipeline on a small scale autonomous systems also, where the LiDAR cannot be deployed. So thanks to 𝗏𝗏, we have a lot of facilities, a lot of funding to procure these kind of stuff. We have practical test spaces to work into this thing. And if you want to scale up your research, then we have the Kinesis lab, where we can do the large scale experiments also. And we have a full playgroup where we can even test our drones and things like this. So in general, overall, I think there is a great potential to test and deploy our research and see that what are the actual environmental factors which can affect that. So having said that, now let me give you a very fast overview of some of the scientific methods, because that would be now important for the audience which is interested in deep down. So for the energy efficient architectures, we are building up our own neural accelerators. We have already two versions of different neural accelerators. This is a massively parallel neural accelerator which has different type of processing areas. It is definitely built based on systolic array-like architecture with different bypass modes. We have developed tools which can partition the processing of machine learning and then do the mapping of that. We have demonstrated that our CNN accelerators, actually, which is quite older now, are already like 2x faster than the state-of-the-art accelerators. We've also built up the capsule accelerators, but now capsule networks are not that prominent, so the transformer is a de facto kind of, in many of these applications. So we have built one of the world's first open transformer accelerators, which is completely fixed point kind of implementation, which also got in news. And this is based on, again, a massively parallel computer array. We have multi-headed self-attention block and different type of, like Mac units. So these are like comparisons that I can share the slides. You can have a look at this, and we have shown that we have built it on ASIC65nm technology, and our 6-tron architecture, for example, is completely integer rate based, and then it can be like much better compared to many other state-of-the-art accelerators which are available in the market. It provides an extremely high throughput, 3 to 4x faster than the recent, at that time, whatever GPU was there, we compared against that, and it definitely consumes, instead of like 250 watts, 200 watts, it only consumes 33 watts, and the accuracy of the transformer model is very, very high, and we have tested for different type of transformer models also. So having said that, compute optimization is only one part since I have extensive work in overall system architectures, we have always advocated that memory optimization should be one of the primary things that one should target. And in fact, memory and compute goes hands in hand, which means that if you are building up a massively parallel computer architecture, you need to design your memory hierarchy also accordingly, which can feed the data in the right fashion, which can shuttle the data from the off-chip memory to the on-chip memory and all the way to the compute elements, and which can massively reuse the data to avoid the excessive off-chip excesses, and this can significantly cut down your memory energy. Depending upon the architecture, the memory power can be 60 to 80% of the total power consumption, which means this is a big rock that you have to also break. So we have developed an off-chip memory optimization tool where we can extensively reuse the input feature map, intermediate feature maps, and a lot of weights. We have also developed an efficient tiling mechanism and mapping on the DRAM in multi-bank DRAM, the sub-array level parallel DRAM. These are like two large DRAM organizations which are available, and we have shown that we can save up to 96% of the energy delay product in DDR3 or SAL, which is a sub-array level parallelism architecture. And these are like all accepted at the top tier conferences and journals, which show that the community is very much willing to that. There is another thing which is called scalable effort computing, which basically means that you can actually change your underlying hardware to tolerate some of the errors which nobody can see actually in real life, and while getting a lot of energy saving. This trend is called approximate computing. There is a wide range adoption by industry and academia, and this research, this is almost more than 1.5 decade. We have extensive work for almost a decade in this area. We have built delivery tools which can do the model compression as well as the resilience analysis of different approximations and their impact on for example, the neurons accuracy. We have developed also different type of number formats and build up the full-scale architectures. We have also developed self-curing blocks, which basically mean that if you introduce a plus one error, then the next block will be giving you the -1 error, and the net error will be 0. And when you deploy them in a multi-die accumulate, and if you're doing an FIR filter or any kind of MAC operation, you know that the goal should be the net error should be close to 0, which basically means that you are giving approximately correct answer with an extreme energy efficiency that you can have. Just to give you an idea, this is a older result. We have, of course, this is, as I said, pruning and quantization, defector estimate for everything. So all the things that we deploy, we do pruning and quantization. So the later demos that I will be showing you for the modern systems, they will be doing all these methods. But just for the sake of simplicity and explainability, I have taken a very small example of an earlier version. And just to show you that there is a potential to actually cut down more than 90% of the neurons, which are not really relevant for that particular use case, and you can retrain that network, and then it can still function very quick, very good, and close to the top one accuracy that you were having earlier. So the quantization is also again a defector standard nowadays. Nobody is working in floating points kind of stuff. You can go up to 16-bit fixed point quantization very easily. Then if your system has resilience, you can go up to 8-bit or up to even 4-bit. And then even there are people are using that mixed kind of quantization, which basically means that some layers, intermediate layers, which are not that important, you can have 4-bit quantization, and the starting layer and the final decision layer, which are like good, you can have 16-bit to 8-bit quantization depending upon the general resilience of the network and how well you have trained. We're talking about the post-training quantization, PTV kind of stuff, but there are also people who are working on, like, you can aggressively quantize and retrain, or you can introduce quantization during the training process, or you can actually introduce pruning and quantization during the neural architecture search process, and all these different variants are available, and they are like widely used nowadays worldwide. And of course hardware approximation gives some extra bit of that energy savings. This is our in-house built complete neural architecture search framework, which is hardware aware, which basically means that you can tell me, Shafique, okay, here is a mobile phone and here is my network specification that I want to solve this classification or detection problem. Can you please generate me a neural network which can fit into this device and then meet my goals? And answer is yes. And this is done typically by neural altering research. What we do is that we define different basic building blocks. We do permutations to build millions of candidate solutions from that block, and then generate those candidate solutions and evaluate them using a genetic algorithm, which is basically NSGA2 variant. And then we output the set of Pareto optimal points, and then you can do an extensive evaluation of those Pareto optimal points and pick the one. The biggest challenge here is building up the core search engine and the analytical models, because you cannot run millions of different neural network combinations on actual hardware accelerator, and the hardware accelerator may not be even sometimes available at hand. So you are doing this in a hardware software co-design paradigm fashion. So in that particular case, what we need is analytical models of performance, latency, energy consumption, and stuff like this. And we have also built our own in-house analytical models for the GPUs, like embedded GPUs, like Jetson, Orin, and things like this, as well as also some things which are running on the mobile phones, like M4 chip and M3 chip and things like that you have on your mobile phones. Having said that, let's go a bit deeper into the security stuff also. So we have built a complete extensive ML security analyzer in our lab, which can actually analyze the security against serial attacks, which are done at the inference time, the backdoor attacks, which are done at the training time, and the model stealing attacks, which are done at deployment time, also in a black box setting completely. Then of course we're looking into some hardware security things, but I'll skip for today's talk. In general, we know that the machine learning, when it's going into a decision making stuff, it has to be robust, otherwise you can make wrong decisions and you will not know exactly that why it was making wrong decision, because you have no idea that someone has perturbed the physical environment, and the data that you are, let's say, using for computing is actually poisonous data. So I give you some examples. Here we have built up a tool to analyze the data sanity. So if you are using your data for training, you have to ensure that data is a clean data. It does not acquire the samples. So we have done a PC-based analysis. So for, let's say, general traffic and additional data set which was poisoned, so we can see that the poisoning of the sample have a completely different distribution compared to the clean one. And similarly, we have done it for C410, and we can do it for the more advanced one. The issue happens when you have bit disparate kind of data distributions, where you have a lot of different types of classes and there is a feature overlap happening. In those cases, sometimes the poisonous data can have overlap, but then you need multi-tiered analysis to go through, and only PCA or ICA kind of analysis won't be sufficient in this case. We built a very big library for serial attacks to analyze the security vulnerabilities of different machine learning algorithms. And you can just simply see security as a service here, and we have a lot of state-of-the-art attacks, and we have a lot of novel attacks that we have developed in-house. I just show you some of the examples of the attack that we have developed in-house. This is a very powerful attack, a patch-based attack on molecular depth estimation, which is very widely used in autonomous vehicles and mobile robots especially. You can see that there is a small patch which is put on this person's bag, and this person is not very clearly visible to the autonomous vehicle or the mobile robot now in this depth estimation, or it is seen very far. So if your depth estimation is used to calculate the distance between objects in driving, then you can see that this object is seen very far while it's very near to you. Same we have done it for the car, same we have done it for the indoor slam and stuff like this. So this is a video of the driving scene, and you can see that this car, for example, is not detected very well, and this is the real, and this is the attack, and the real, you can see that the car is becoming closer, while here the car is not becoming closer, rather it looks very far for you. This is also one of the very powerful attacks that we have demonstrated at CVPR like about 2 years ago. Victor, one of my students, he has implemented this attack on the person detection systems. You can see that he has printed this dog or a cat, whatever image you give him, he adds a very small invisible noise into that. Whenever he hides the dog, he is visible. Whenever he unleashes the dog, he is not visible. At that time, the state of the attack was that you have to stand straight in front of the camera, but now he can stand at any angle. He can create freezes. So basically what we have done, we have modeled different types of affine transformations, expectation over the transformations kind of stuff, and he has also modeled the freeze transformations, and he has modeled other kind of brightness and and variations, and then integrated in an in-loop optimizer and generate a noise which can then be integrated into the given object. There is also one more model which is important here, because whenever you're generating a digital image and put it on a shirt, there's a color converter, so that kind of degradation effect is also included in this attack, which basically makes it very strong attack actually. And we are also working on the defense pipelines. I will skip that kind of part for today, but just give you an idea how a defense pipeline looks like. The defense pipeline works in many different ways. One that I showed is the data sanitization, so that is done for the poisoning attack. But you can also develop retrofitted pre-processing pipelines. Many of the dispersed noise attack can be removed using specialized noise filtering. Many of the non-robust attacks can be filtered using a fine transformation and quantization. But then other kind of attacks can be detected or eliminated using post-processing kind of methods also, and this is what we have been actively looking into that. This is one attack that we have developed on dimension reduction-based attacks, which we have developed for topic detection and classification problems. Here you can see there is a grand cam view of this image. So here there is a fish in the hand of a person. When we are dispatched, then the fish is not detected, rather something else is detected, and we know that the patch has created the focus on the important features somewhere else. But once we reduce the dimension reduction, we deploy the dimension reduction on the input space, then the important features are being learned, and the focus comes back to fish, and it's detected as a fish. So there are a lot of these kind of things that can be done. Of course, every defense comes with a certain cost, and there is no single golden silver bullet here, or golden defense mechanism. You have to implement a multitude of defenses, because there are different philosophies of attacks that people are working on. There is attacks on the detection mechanisms. There is also this other stuff that we are working on is on anti-weather kind of forecasting. This is the full-scale detection and lane detection system. Here is the anti-fogging system. We can actually clean up the fog, get the clean image. We are currently working on an extremely dense cloud fog. That's the second version that one of my team is working on. And then we can actually put this on a mobile phone, which means that it's weather filtering, detection, distance estimation, and quoting on a mobile phone, so that even if your car does not have this feature, you just simply install this app and then can start using it, like making your car kind of a semi-autonomous. It's more like a recommendation to the driver and stuff. While the upper system that you have seen is basically extremely robust in different lighting conditions and stuff like that. Now we are building up a multi-task solution, which means that one single system can do all these tasks, because you cannot afford 10 different models on your mobile phone running in parallel. Having said that, we are also looking into other kind of security issues, like for example, there is a large language model based deepfake detection. This is the ICCI detection, where you can give a picture of a rose, ask is it natural or fake. It will tell you that this is a natural image, it's not a generated image, and it tells you the reason behind that. We have developed different model variants, and we see that the reasoning can change depending on the model quantization and stuff like that. And this dog, for example, is a AI generated image, and there is a reason behind that. We are currently working on a very advanced version of this thing in an agentic format, which means we are building a forensic agent, and forensic agent can actually give you better reasoning and better detectors also. We have also developed an agentic system based on Quen to do deepfake detection. This is a video and image deepfake detection. Currently we are working on audio stuff also, and then we're going to integrate. It can give you reasoning, which frame has been manipulated, where it has been manipulated, and which kind of filter it has been manipulated, most probably like frequency domain or spatial domain filters. And then we can actually give you very robust answers for that. We are actively looking into large language models for jailbreaking also. This is a very important threat on the models. So earlier, as I mentioned, the serial attacks, packet attacks are more important for the deep neural networks like CNNs and transformers. For LLMs, the biggest attack is the jailbreaking attack, which basically means you ask a malicious question to any large language model, and it gives you the answer which it is not intended to give you. So we recently have a ICCI paper accepted metacipher, which is one of the latest and most advanced jailbreaking attack, and this is a learnable attack, which basically in modern age is that if you do a jailbreaking in, let's suppose, any state-of-the-art stuff, then it can learn in 1 or 2 months, and then it defines the guardrails and stuff like that. But we have an RL agent which can learn on the fly different type of ciphers, and it keeps on updating as the defense is also updating. So the whole idea of these jailbreaking attacks for us is to understand the vulnerable space so that we can design the guardrails. Some of the videos building up the just skip through this kind of stuff, and let me show you the videos of some of the stuff. This is a very nice project that we are building up, which is a mind controlled cognitive art. So we have built up this complete thing in house, from mechanical components to all the way up to the intelligent components, for example, and the electrical components like the motor integration, controlling your brain, controlling through gaze and stuff like that. So I'll just show you a video of that, which we showed in Make It an Emirate series, and it also got international news. And we are currently showing this in another exhibition today in Abu Dhabi also. So we are using it for example DC ultra cortex, but ultimately want to extend that and use it for example like headset kind of based things. So this whole all the primitive operations that we are doing is like my student is thinking, and then it's taking action. It can move the hand, it can make different operations like rest in bottle. It can look at any location and the arm is there. So this is a gaze-based kind of movement. There's a little bit latency because at the moment functionality is the biggest thing that we are making it perfect, and then later on we'll do the model optimization for the no latency in the second round. So we have now this is the second generation. Fourth generation or because currently we are optimizing the mechanical models mostly, and now we have the joint in the shoulder. For example, with the full 36 degree of freedom. I don't know exactly the number, but it's a completely G1 compatible arm like the G1 humanoid has. These are like different mobile watch. I already showed you that. Skip through that. This is an autonomous slam kind of demo where I can show you that this robot can completely do the slam autonomously, build up the map of the area. I think the more important stuff that I'm going to show you is this VLA. For example, this Limo, you can give the command to Limo actually text or voice, and it can do the task. But there is no explicit programming of this thing. There are like 4 different machine learning models working on this collision avoidance detection, and a tiny VLM which is operating there is a grounding Dino actually integrated them and operated them. So just to tell you that what the different person is doing is doing frontier exploration, mapping, path planning and optimization. So this is the kind of stuff which can do autonomous reconnaissance for you, it can do patrolling for you, it can do also localization for you and things like this. Once this is functionally complete, we will also do the complete security analysis of that and make it much more robust so that none of these objects go evaded by adversary, for example in your maps and things like that. Across the medical projects, we have worked on the medical projects on hand and ultrasound devices together. Healthcare, we are looking into the extremely compact models for X-ray detection. We have end-to-end system for multiple sclerosis, brain MRI detection. We have a backbone based on different type of segmentation networks and detection networks. We are doing a lot of input pre-processing for data. We are working on a lot of metric evaluations and post-processing, doing a longitudinal analysis, and we are also building up a fine-tuned LLM to give you the answer. So let me give you just a very short demo of this thing. It's based on tiny lava mat, but we are now looking into more advanced models for this thing. You can see here is that this is running completely on Jetson Nano. You can give an X-ray image, ask a question, it can start answering the question. This is on the back end connected to a PubMed dataset, which is one of the largest datasets for the publications, medical publications. It gets you the answers the recommendation from there, and on the back end we are doing our own segmentation and things.
It's implemented on the NVIDIA.
And this is another government kind of project where we are basically extensively adding different type of medical data sets for simple queries that we will be having regarding your medical diseases or symptoms and stuff like that. It can tell you that what kind of prescriptions can be done. So these kind of tools can be used by doctors as well as the patients, and this is what we are building up. This is just some of the results of this Keynote project, where we can show that we actually achieve better accuracy compared to the state of the art. When doing the longitudinal analysis, we figured out that the state of the art metrics like dice scores are not really good. So we are working on new metrics for this, but this is still like ongoing work, so I cannot show you the results until we publish that. I think I can stop my talk here because I'm already over time, maybe almost done. But we do have a lot of research in quantum machine learning, ETA for quantum computing. We're building quantum circuits, we're building up noise tolerant quantum circuits. I have a team of around 5 postdocs and around 10 student RAs who are extensively working in this thing, and we have published at the top tier venues like IEEE Quantum Computing, QAI, and top quantum titles this year. And the team is extensively looking into industrial collaborations with 𝗤𝗂𝗏, Quandela, who are like really doing a lot of practical quantum applications and logistics and stuff like that. So I think I'll conclude that here. I would give you an idea that besides building up the practical systems prototype, our team has also succeeded in publishing at top tier venues like CVPR, IIII, ICML, ICCI, DAC in terms of systems, and IROS in terms of, for example, robotics, UCE, and QSW in terms of quantum. So with every field we typically target the state of the art. Of course, thanks to the team members, they're extensively working day and night, and a lot of student RAs who have been also extensively supporting us in initial proof of concept studies, in demonstrations. And some students are really very smart, and they take the work forward beyond even our expectations. That's it from my side. I just want to pitch you something which I think every year we might be doing. We recently did a vibe coding hackathon. A lot of students from Pakistan and non-civil actually participated there. We will be hopefully organizing this next year also. This year we did it together with our colleagues in Shanghai. The winners also got some award, and it was very interesting competition. We got like more than 200 teams registered for that. At every year we have a security challenge also, CSI event, which is recently just concluded, but next week will begin in November. But then there is another hackathon, which is one of the largest hackathon worldwide, and this is the largest in the MENA region. And I will appreciate that a lot of students from Pakistan also come and participate in that. These teams are typically very interdisciplinary. So in these hackathons, now I think it's in April, so the nominations are open for the quantum hackathon. So please participate in that. This gives you a great perspective to look into challenging problems at the student level, build up the teams, interact with the international students, and it's in the close vicinity, like it's not far also from the region, so you can easily come back and forth, and that's also good, I guess. I'll share the slides to get the link of all these contact persons, and then you can coordinate with them. Thank you very much for now. I'll stop sharing my screen, the slides, and if you have any questions, feel free to ask me. I'm here.